What's up, AP Physics people? Okay, so let's jump back into another problem and go through and look at this. Like we are on the topic of centripetal force and acceleration in circular motion. So let's just jump right into it. Okay, so here is the question. We have a disk with a coin on it spinning around in a circle. We're given the mass, we're given the radius where the coin is, and we're also given that it doesn't slip and that it goes in one complete revolution in 1.5 seconds. All right, so right here, the first thing it asks for is, for us to determine the linear speed of the coin. And well, first we have to draw some vectors on here. All right, so draw and label the vectors for the acceleration. So we're going to do the instantaneous acceleration and the velocity vectors. Okay, so let's say right at this moment, it has a velocity and it has a tangential velocity, and that tangential velocity is going straight away from it. So you can think of like what would happen if the turntable would just completely move away and that coin would be moving forward. Note that we don't have, this isn't a force, this is a velocity vector. Okay, in acceleration, the acceleration vector, well, we got the acceleration vector is going straight towards the center. Centripetal force acceleration vectors go straight towards the center. All right, the next one, determine the linear speed. So the linear speed, that's another name for the tangential velocity. Linear speed, tangential velocity. And we have to relate this to an equation. So here is my equation. All right. So here I have omega. Omega stands for the angular speed. So what's the angular speed? Well, the angular speed is the delta theta over t. All right. Well, if we look at how far this thing goes, and let's do this. Let's just plug in some numbers here. So we have r. We were given r up top, so we were given r as 0.14. Delta theta. Well, delta theta is 2 pi. And that's in radians. It goes around 2 pi radians. And then the time it gave me was 1.5. So if I do that math, I get 0.59, I think. And that would be in meters per second. Because this is in meters and this is in seconds. And we don't, rads, like we're not going to use that. That unit doesn't end up calculating out. So we just have meters per second. Okay, so next, the rate of rotation of the disk is gradually increased. The coefficient of static friction between the coin and the disk is 0.5. Determine the linear speed of right before it starts to slip. All right, I'm going to switch colors here. All right, so let's go through here. Now we have, it's a little bit trickier. So now we're going to have let's draw a force here. So I got my coin. I'm going to draw my centripetal force. Okay, now I know that I'm going to sum my forces and set it equal to mass times acceleration. But since this thing's going in a circle, I'm going to set it towards my centripetal acceleration. Well, what's the force here? This force is the force of friction. Friction is what's keeping it going around in the circle. So here I have force of friction is equal to mass. Now my centripetal acceleration, We need to relate this to my velocity, because ultimately I'm solving for this velocity here. And the equation for centripetal acceleration is v squared over r. Okay, so frictional force. We have to know that the frictional force, well, that equation is my coefficient times my normal force equal to mv squared over r. Well, my normal force here, this coin is not flying up off the table. The normal force is pointing like straight up, like vertically out of the page. And the weight's going straight down. But since it's not going up or off the table, this is mass times gravity equal to mv squared over r. All right, if we look at this, now we just have to rearrange this. We know my mu, g we know is 10, and we know our radius. So we can rearrange this, and note that we don't even need my mass here. The mass cancels out because we have mass on both sides. So if I do a little algebra here, I can rearrange that, and I can get, let's multiply this r by both sides. So that would be r times mu times g, right? V squared. So I want to get the v by itself, so I'm going to take the square root of that. So now I can plug all that in. So that would be the square root of 0.5 mu. So whoops, that was my 0.5. So let's take this one step at a time. So r was 0.14, same r that we had here. Mu is 0.5, and g is 10. Okay, I plug that in, and I get 0.84. And velocity, so it's meters per second. Okay, let's look at D now. I'm going to erase all this. Well, that's going to take a while. I'm going to erase all of this stuff. Let's get the big eraser. Okay, so let's go to the next part. All right, it says for D, if the experiment in part C were repeated with a second identical coin glued to the top of the first coin, how would this affect the answer to part C? Explain your reasoning. So let's just write this real quick one more time. So we had from above, we had mu s mg and mv squared over r. So you can see, since mass is on one side of the equation, it cancels on the other side of the equation. So mass doesn't matter because they cancel each other out on both sides of the equation. Okay, let's look at the next question now. So let me erase this, and we will go to next question. All right, so in this question we have a roller coaster car. It's going down the roller coaster and up over, it's going to crest over this top, and it's saying that this is a circle, like this is a arc, this is part of a complete circle. Okay, so we're given the mass of the cart. We're saying there's no friction. The car is given an initial speed of 1.5 meters a second, so it has a velocity here. The hill is 2 meters, and this is 1.9, and then the radius is 0.95. So, all right, the first step, it says calculate the speed at A. All right, so to do that, this is a conservation problem. So we're going to have conservation of energy. So that says the initial energy So the initial energy is equal to the final energy. So the initial energy, what kind of initial energy does it have here? Well, it has a velocity, so it has a kinetic energy. It has 1/2 m, and I'm going to put v0 squared here. But it also has a potential energy because it's at a height. So we have mgh. I'm going to put h1, start off like, we'll say that that's h1. Okay, the final energy. Now, it's going to have, like, we're looking for the final speed at A. We're looking for what is the speed right here. So if it has a speed, we know it's going to have a velocity. And it has a height here, so it has a potential energy. So we're going to say mg, and I'll just call this h2. Okay, this is kind of cool. Mass isn't everything, so it turns out mass of the roller coaster doesn't even matter. So I'm trying to solve for v here. So now this is just about going in and plugging in the numbers into the equation and solving for v. So I'm going to do that like really quick. I'll make it red. I'll let you guys do the math here. But so here we have 1/2. We have v0, so 1.5 squared plus g is 10. h1 is 2 equal to 1/2. Our v, that's what we're looking for, v squared, plus g is 10, and h2 is 1.9. All right, got to do a little bit of algebra. I'm not going to do all the steps here, but if I can combine these, I can do the calculations out, subtract this, and then I end up having to take the square root, but this is what I get. I think I get something around v is equal to, it's right around 2 meters a second. We're going to say 2 to keep the numbers simple. All right, so we have 2 meters a second. Okay. Next part of this question. On the figure of the car below, draw and label the vectors to represent the forces at point A. All right, so we got to know the forces at point A. I'm going to actually do it for the, I'm going to come up here. It says draw right on the diagram, but I'm going to do it right here just so I have more space. Okay, so what force do I have here? Well, I have gravity, I have mg, and I also have another force. I have the normal force. I have my normal force. And this normal force is actually going to be a little bit less than this this weight. And you can think about that. Like if you're going fast and you're going to go up over this the top of this peak, you're going to feel like you're going to feel a little weightless. So that means that the track is pushing on you less. So there is my free body diagram. A lot of people might think like, oh, it's going to the right. It's got to have this force going to the right, like an applied force. But that's a common mistake. There is no applied force to the right. Okay. So, all right. So D is asking for, or C, sorry. C is asking for the magnitude of the force on the track at point A. So it's asking for what is the magnitude of the force. All right, so let's come over here and we're going to sum the forces, set it equal to mass times acceleration. Well, on here, I'll draw it right here. We had the normal force and we had mg. So my, we'll say up is positive. So I'm going to say positive Fn minus mg is equal to my mass. But note that the acceleration is always down, right? So since I'm picking down as positive, down as negative, I'm going to have a negative AC. Okay, I want to solve this, but I know what let's come down here and I'm gonna write it down here. So instead of AC, I'm gonna put the V squared over R because I was given, like I solved for V before, and I know R. Okay, so all right, it says the magnitude of the force of the track on the car. Well, that is your normal force. So this is kind of tricky, but we're looking for normal force here. Normal force is the force of the surface pushing on the roller coaster. So if I'm going to solve for normal force here, I'm going to add mg to both sides. So I get mg minus mv squared over r. Okay, and I would let you guys go through and do the math there, but you know mass, you know gravity, you solved for V before, and we know R. All right, so D here, in order to stop the car, calculate the work done by frictional force in order to stop the car. All right, let's switch the color here again. Oops. All right, so I'm asking for the work. Will work, the amount of work that it's going to take, this is the work kinetic energy theorem. So work is equal to the change in kinetic energy. So if I think about that, the change in, that's going to be 1/2 mv squared. So this is, let's say that this is V final minus 1/2 mv initial squared. Okay, well, think about this. The final velocity, if it's coming to a stop, that's 0. So what I get here is that the work is equal to negative 1/2 mv squared. And this v is going to be at whatever velocity you solved for above. So I think we said that that was 2 meters a second. That's however fast it's moving. And note that the work is negative because it's taking energy away from it. Okay, last part of this, let's look at that. The last part says, explain how to modify the track to design the car to lose contact with the track at point A before descending down the track. All right, so let's think about this. What I want to do is I want to figure out at what point would the normal force go away. So I wrote it really small here, but let's say like at what point will it equal to 0? So when is the normal force going to equal to 0? Like what would I have to do to the track? So I'm going to write my the equation that we had before when we solved for normal force. Okay, so if I want normal force to be 0, this thing right here has to be as big as possible so that mg minus this, like the bigger this is, the if I subtract mg minus this, it will equal to 0. So I want this to be big. Well, what can I do to make this big? Well, I can decrease r, because decreasing r, something on the denominator, makes this bigger, or I could increase v. So that's my two things. So what I could do is I can, to increase v, you can think of, I can increase V by, well here, let's just show it. I think it'll be easier to show right here. So what's one way that I can make it faster here? Well, to make it faster, I could lower this. So I could lower the track. So that would be one scenario. Or I can make this a smaller radius. So I could make it come down here and go with a smaller radius. That was really bad. So I can make the loop with a smaller radius. All right, so this is a tricky question. So hopefully you guys were able to get it. Okay, good job, physics people.